Hello, hey everybody. We're going to continue talking about projectile motion. I hope you survived the midterm okay. But we're going to be talking about similar but different now. Um, and so consider the following just math problem. So instead of jumping into work and energy and saying, oh, there's this vocabulary word and this vocabulary word, consider the following mathematical problem, which is that you're launching something at some angle, and there's some position x as a function of time and y as a function of time. There's also the velocity as a function of time. Is there any combination of these variables that adds up to a constant? So in other words, that no matter at what time that we're thinking about the position of this object, is there some combination of these things that adds up to a constant? And the reason that would be helpful is because there's often situations where we know like this and this, but not so much this, and we'd like to figure that out. So if by some chance these could all add up to a constant that is the same constant throughout the entire trajectory, that would be very helpful for a variety of problems that we need to work on. Is there a combination? So without letting you guys spin your wheels on it at home for a while, I'll show you what the combination is. Okay? And so, which I'll do in the next slide. In this slide, I'm just going to show you the equations we've been talking about so far. By the way, my cat wants to be in the video, by the way, so he might show up in a second. He's right over here. There he is. Hey, buddy. All right. So, so we have the height above the ground as a function of time, right? So if g is positive 9.8, then we can go ahead and put a minus sign here. If you have some initial y velocity, right? Maybe you do, maybe you don't. But if you do, then you got to put that into here. As the thing moves with time, there's some initial height, so on and so forth. And we also know that the velocity is a function of time in the y direction. The vertical velocity depends on what the initial velocity is, and again, g is plus 9.8, so we're going to put a minus sign here, minus gt. Right, so 9.8 meters per second squared. Every second that goes by, the velocity drops by 9.8 meters per second. Okay, so those are the equations for y. If we're moving in so for projectile motion. There's also this equation that we talked about. We found this equation essentially by solving for t, subbing it into here to create an expression that only depended on the velocity and not the velocity and the positions, but not the time, because often we don't know how much time something is going to take, and so this equation has a nice format to it where the time variable does not explicitly appear. Now, usually when I'm talking about this equation, I say this is y final, this is vy final, this is vy final here. It depends on what your definition of final is, so you can also replace that just with y as a function of time. So is anything really final? Well, we can just say whatever time of interest. So hopefully that's not too much of a shift in thinking. By the way, this delta y here is y final minus initial, so that's y as a function of time minus the initial position. I think we'll get to that in a moment. Now, if we're doing projectile motion, there's no acceleration in the x direction, which means that the equivalent for x, we don't have to worry about this acceleration term. So the only thing that's left here is like this. And then, again, if there's no acceleration in the x direction, that means that the initial x velocity, the initial horizontal velocity, is the same as the final horizontal velocity, which we saw that with that one interactive where you click on the basketball that's moving and show that the vertical lines stay about the same spacing, whereas horizontal lines, that the spacing does change. So those vertical lines keeping the same spacing shows that the horizontal velocity is not changing even as the object is accelerating in the y direction. So these are the equations that we have, and the challenge is to combine it into something that adds up to a constant, even though this is changing with time, this is changing with time, all these things are changing with time. So without just letting you try to guess, I can tell you what it is. The claim is that this combination of things adds up to a constant. In other words, something that does not these things which do depend on time adds up to this thing which does not depend on time. And so let me try to show to you that indeed this is true. So the first thing to do is actually the easy part, which is that our Vx as a function of time is not actually changing. So that's the easy part, which this is not changing with time. So that's pretty easy. But the rest of it we do have to worry about. So we're going to substitute it in some of the equations that we just looked at. So we have, in particular, we're going to sub in the Vy as a function of time. So we saw in the previous slide that it was this. So that's what we have so far. The Vyi does not depend with time because that's just the initial velocity in the y direction. The Vxi does not depend with time because that's the initial velocity in the horizontal direction. So right now it's not so much looking like it's going to add up to a constant, or it's looking like there's still some time dependence here. But if you realize that there's time dependence in here, right, because this is the final y versus minus the initial y. Delta is always final minus initial. It's never initial minus final, by the way. And so this is the same thing as this, and so I can put that into here, right, because our final is sort of the current time. So I can stick that into here, and if you multiply all this out, right, so there's a 1/2 m, so 1/2 times 2 is 1, m times this, so there's an mg, so you end up with minus mgy as function time. And so if you work all this out, you'll find that essentially that this cancels with that. Right, so you multiply these things, so 1/2 times 2, the 2 cancels, again, minus mgy as a function of time plus mgy as a function of time, well, that cancels out. You end up with this, the initial height, that's a constant, that doesn't change with time. The initial height does not change. The height changes with time, but not the initial height, right? The initial velocity, the velocity changes with time, but not the initial velocity, right? So we've managed to show that this thing, which has a bunch of time variables, ends up being equal to something that does not have a bunch of time variables. That's a very healthy thing. That's a very helpful thing to find out. Right, Polo? Yep, Polo the cat, he likes that. Hey, buddy. All right, so we are going to call this constant the energy. As many of you probably already guessed, we're going to call it the energy, but that's what it is. We're going to call this term the kinetic energy. This v squared thing technically is the magnitude of the velocity vector squared. So technically that's also the speed squared. This term, the mgy, is the potential energy term. And so the kinetic energy plus the potential energy adds up to the total energy, like that. So a fun thing to do is to play around with this demo, which I didn't make, but I know some of the people that did. And so you've got a skateboarding situation here in which, what you want to do is you want to click this skateboarder and put it up here and then let them go. It's important to turn on the bar graph. And so the idea of this is that initially, when the thing is at the very top, the kinetic energy is 0, and all that energy is put into potential energy. So if I can, so I put the person at the top there, it's all potential, and then as it moves, at the very bottom of the ramp, the potential goes to 0, and all of that energy is transferred to kinetic. And the important thing is that if you add both those together, it adds up to the total energy, and the total energy does not actually decrease. Now, we all know that that's not 100% accurate, right? We know that there's friction in the world. And so what does that look like in this case? Well, if you include some friction, then again, you put the person up here. Initially, all the energy is in potential energy. And then you let go, it's going to convert, the potential energy is going to convert to kinetic, but some of it's going to be converted into thermal energy, right? Friction involves things getting heated up, and so we call that energy loss to thermal energy. So, and we also know that friction over time will bring objects to rest, and so over time, the amount of energy in thermal is going to get larger and larger and larger until eventually all the energy is used up, and the thermal energy equals the total energy. And there's other fun things like, the thermal energy increases whenever the velocity is largest, because that's when, the friction is most important. If it's just sitting there, you're not losing energy of friction, right? So there's a lot of fun stuff that this illustrates. All right. Let's see. So before I get much further with potential energy, I have to confess that when I was in your shoes in college studying physics, I thought the word potential energy was just sort of a bit of jargon that didn't, I don't know, just words. I mean, it didn't really mean a whole lot to me. But I actually think it's actually a pretty good description of what this quantity is, which is that it is a kind of energy that can be converted into some other kind of energy. So for example, it's converted into kinetic energy. You can imagine converting into other types of energy as well. So the phrase potential energy is actually not the most jargony, specialized term I've ever heard. Plenty of other good examples of that. So for example, my electric car, I have a Nissan Leaf. The braking system has a capacity to convert the kinetic energy into electrical energy, and then that electrical energy can be stored in the battery, ultimately in terms of chemical energy. Or if you imagine someone is, let's say that they're jumping from, the first floor of a building, and they land on a spring, they compress the spring. Well, then that person's converted their energy into spring potential energy. That's another form of potential energy, sometimes called elastic potential energy. We'll talk about that later in the lecture. We've been talking about energy, we haven't given it a unit, so we'll discover that the units of energy are a Newton meter, not just a Newton, but a Newton meter. And because we know Newton's F equals ma, so 1 Newton is 1 kilogram meter per second squared, so that means that 1 joule ends up being kilogram meter squared per second squared. We'll talk about this equation for a bit, which is that the force, the energy that's involved in some kind of motion has to do with both the force and the distance. And so if you apply a force and you don't actually move at all, then potentially then that doesn't necessarily mean that there's any energy that's used up. So that's a little bit strange for us because, we humans, when we push on a wall, I have a wall behind me. When I push on this wall, eventually I'll get tired of pushing the wall. My arm will get tired and I'll kind of give up. And that is because it takes energy and calories for me to be able to apply forces to things. But nature is not like that. So nature, so for example, if you put a spring here that's compressed, that's pushing this block, that spring will sit there pushing the block for a ridiculously long time. Maybe even an infinitely long time. Or for example, if you put a positive charge here and a positive charge here so that they're repelling, those positive charges will repel each other for the rest of time. Even if it doesn't move, they will continue to repel each other. They don't need energy to apply a force to the other thing, which is what we do. The sun does not get tired of applying the force of gravity to the earth, and thankfully for us, right? So it's unique to humans that it takes energy to apply forces for things, but in nature, that tends not to be what happens. So that's why it makes sense that only when things are moving is that actually the situation where energy is changing. Force over distance. So as Yoda would say, there's do or do not, there is no try with this thing. Now in the book, it talks quite a bit about this problem in which the force is at a distance and the object is moving along. And so you'll see this equation. The important thing about this equation is that the delta x is the distance that the thing actually travels. And another important thing is that because it's an f cosine theta, that means that the component of that means that it's only the horizontal component of the force, right? F cosine theta is the horizontal component of this force. And so this equation only makes sense if it's the horizontal component of the force that's doing the work. The vertical component of the force, which is real, right? So when you're pushing down an angle, part of that angle is pushing down. That does no work at all. Like F sine theta, there's no work associated with that. Because they're not actually managing to push it downwards, like, and have it actually move. I think I just said all these things. Yeah, and including friction does not actually change this equation. The only thing that friction might do would be increase the force that's required to push things across the floor. Usually when I'm in the classroom, I have like an eraser on a whiteboard and I push the eraser across at an angle. So the last thing to notice is that this does not actually depend on speed. So if I had my little eraser on my whiteboard and I was pushing it across, I can push it across fast, I can push it across slow. The force that the eraser is pushing back on me is not changing, right? If I make it go faster, then I'm not necessarily using up any more energy, but it might be hotter. Like if you had an infrared camera, you might be able to see how the board is a little bit hotter if I go faster. That just means that the energy is being used up quicker. That doesn't necessarily mean that the force is increased or that the total energy is more. Going the same distance, of course. All right. I think I said it earlier that friction makes things hotter. I think I just said that. So whenever things are hot, so basically we haven't really talked about what temperature is yet. We'll get to that later in the course, but suffice it to say that temperature involves either vibrations, so everything is sort of vibrating at some distribution of speeds. The air in this room, if you make the air in this room hotter, it will zip around a little bit faster. We'll talk about that a little bit later. And so that's part of why there's a connection between friction and kinetic energy and things like that. So if this is our total energy, E0, then we have kinetic and potential and thermal. And these things are all potentially changing with time. The total energy is not. So there's some clever things that we can do to this equation that might be helpful later. I know it seems like a pretty simple equation, but there's some clever things that we can do. So again, this is at any time t. Maybe I should put time subscripts on there. But because this is true, and this is true at any time, that means that it's true initially and for the initial quantities, and it's true for the final quantities. So for example, the initial kinetic energy plus the initial potential plus the initial thermal energy adds up to the total energy. Often the initial thermal energy would probably be zero if we haven't used up any energy for friction. And then it is also true that the final kinetic plus the final potential plus the final thermal adds up to the same constant. And so what you can do is you can, because this is true, that means that what is essentially E0 minus E0 equals E0 minus E0. Right, so this is 0 equals 0, right? But this is, if you consider that this KE final minus KE initial, that's delta KE. PE final minus PE initial, that's delta PE. And then delta thermal, that's E thermal final minus E thermal initial. So from this thing, you can find this thing. And I think the book likes to think of it in these terms. For example, that if your kinetic energy is going up, if your delta K is positive, then your change of potential energy is probably negative. Things like that. So this is sometimes a helpful equation for answering questions. So let's see. So this is an interactive, which actually the worksheet is based on, which is this. And I don't know why I have two slides there. But allow me to demonstrate. The question that this interactive raises, I didn't make this, is from the book that you paid for, so getting your money's worth. I think they did a pretty good job on this. I have to give them a hand. So I'm going to open this up in a browser, and the question is, does the launch angle affect the final speed? So the current speed is here. And by final speed, a lot of these problems, you think that the final speed would be 0, right? Because it's landing on the ground. That would be the obvious answer. But no, what they really mean is the speed, the moment before it hits the ground, I should say. So let's go ahead and click this thing, see what it does. Alright, so here we go. Now it is currently at an angle of -15. It's going to start out with some kinetic energy after I press start. And you guys can feel free to play with this at home, because the link's in the slides. There's some amount of potential energy because we're up on top of a building. And it tells us the initial speed is 12.5 meters per second. You can see that it's also 12.5 here. Time is 0, height is 25.5. And so we're going to go ahead and press start, see what happens. Alright, so the thing launches. You see that the speed is getting faster, right? Initially it was 12.5 meters per second. Now it's 25.61 meters per second. The question is that if I change this angle, how is that going to affect the final speed? So let's say that instead of shooting it down at 15 degrees, I want to send it up at 30 degrees. I feel like if I did plus 15 degrees, you'd just tell me that there's some coincidence. But alright, so now we're going to do up. The initial speed again is 12.5 meters per second. And specifically, this is the speed that it's launched at. Right? And then we're going to see what happens then. Alright, so here we go. So we're launching it, launching it, launching it, launching it. Do you think it's going to be faster or slower? 25.61. It's the same. What? Alright, let's try this again. By the way, 3 seconds for this one. I forget what it was for the other one. Okay, so I'm going to set it to 0. See if this works out to be the same. Alright, so 25.61 is what the other two did. Let's see if that happens for the one in the middle. Faster. 25.61 again. What? Okay, a couple of things here. Alright, so the speed is the same. For each of these three, the speed is the same, and I implore you to play with all the different values and show that indeed the speed is the same here. Is the time in the air the same? No. So this one is 3 seconds. This one is 2.28 seconds. This one I'm willing to bet is less than 2.28 seconds. So if I do -15, and do that again. So the other one was 2.28 seconds. This one is about 2 seconds. So no, the more the angle is towards the ground, the less time it spends in the air. But shortly before it hits the ground, the speed is going to be ends up being the same. Even though the time in the air isn't the same, the speed ends up being the same. The last thing to say about this is that the speed is the same, but are the x and the y component velocities the same? The answer is no. No, the x velocities and the y velocities can be very different. So, for example, if I would aim this thing all the way down at 45 degrees, that's going to have a very different the x velocity, the initial x velocity of this thing, for example, the final x velocity is going to be much less than, say, the thing in the middle where it's all horizontal initially. So that's going to be, so the x velocity and the y velocities are all pretty different, but the speed, remember, is the square root of vx squared plus vy squared. So the speed ends up being the same even though the x and the y velocities don't end up being the same. Okay? So the worksheet for today involves running the numbers on all this, using methods that we could have used on midterm 1. Maybe we did use on midterm 1. And then towards the end, we're going to look at it from more of a kinetic and potential energy perspective and use that to show that the final speeds are the same. And you'll find that, I don't know why I'm out of focus now. And you'll find that that it's a lot easier to use energy conservation to come to the same conclusion. You having fun?